Welcome to my material science class. If you are not part of this class, actually physically present in the classroom, but watch it on YouTube wherever you are on earth, this video deals with material science, and within the big topic of material science, a lesser topic is properties of materials that describe how materials behave. And within this discussion, this lesson is the first. It's not quite an introduction to properties of materials, but this is certainly an introductory lesson. Going to take about 30 minutes like I printed over there. In this lesson, we'll deal with 8 words. Only 8. We'll define them, but most importantly, I will explain how these words relate to material science and each other in this material science context. Because they are not just isolated definitions with nothing to do with each other. No, they link up and form a logical chain that's related to materials behavior very specifically. None of these words are used the same way as they are in everyday usage. So, although I don't know how often you use malleable in everyday English, so all of them will be defined, but that doesn't take long. But especially I'm going to focus on linking these up into a chain and explain how they interrelate in the context of material science. So, because it's terminology, we'll do a little bit of grammar and logic. Not too much grammar, but it's gonna help you understand how these words are used and form this logical chain that describes behavior of materials. So, straining is not something you do in the kitchen in material science. There are no kitchens. There are labs, but not so much kitchens. And in everyday usage, straining is a verb, that's an action being done with vegetables and a sieve, and not happening in material science. Completely different. Plastic is not going to be a noun, as in plastic bag that you put in the trash can. It's going to describe a behavior of material, the material's plastic deformation, namely. So likewise, strain is going to describe the material straining, whatever that is. Definitions coming up. It describes, all of these describe the material's behavior. Stress in the corner is not the everyday stress. You're stressed out because you're late, missed your lunch or missed your bus or whatever, and you're stressed out. No, it describes the material's behavior, and the materials are the focus and the subject of these terms in this context. So let's get started. How these 8 are organized. They all start with forces. Forces in English can be of 2 kinds. You see, forces are the cause of things, the great movers that drive material behavior. Forces can be either a push or a pull. Those are plain English words, and their meaning is unchanged. However, in material science, they are not used. They are replaced by Latin equivalents, by Latin variants. So instead of push, the word press is used, as well as another variation of press, compression. Press is the verb, the action word. Compression is the noun that describes the result of the action. And instead of pull, another Latin word is used, tension. Okay? Pull and tension are synonyms. They can be used interchangeably. Synonym means that they have the same meaning, but they're different words. Compression and push are synonyms. They are interchangeable. But in material science, they are not. Nobody uses push and pull, so that's why everybody just uses tension and compression. the adjectives of compression, so compression is the noun, the adjective is compressive. So we'll have compressive forces, and the adjective of tension is tensile. So we'll have tensile force, tensile strength, whatever. Okay? So those are noun, tension, adjective, tensile. Noun, compression, adjective, compressive. Forces, this describes the direction of the forces, and I'm not going to discuss anything else about forces. They also have a size, they also have a unit of measure for measuring. We're just dealing with the direction of forces. It's either coming at you or going away from you. There's no other way. And these are forces just solo, just alone with nothing else. So these are the forces that are acting upon materials and then will generate in the materials an equal and opposite reaction. So the reaction side is over there. How the reaction is generated is through an effect. Let me write this one here. So when a material is being when a force is being exerted on a material, its effect is that the material is in pressure, pressure, or being compressed. That's also can be used here. And when a material is in tension, the result, the effect of this is the material is in stress. There, stress. Definition for stress, those of you in my class, write it down. Definition of stress is tensile force. Okay, that's the simplest definition, tensile force. Okay, so you can use those interchangeably, stress and tensile force. Now, I'm just going to have one sentence for everybody else on the internet. Pressure will be defined later as redefined as a unit pressure, a quotient of force and area, and stress will also be redefined later as a quotient of force and area, but the force in both of these are going opposite ways. But that's unit pressure and unit stress, don't worry about it. From the definition, the quotient of tensile force and area, we'll just cut away everything and just would keep tensile force. So that's your first definition there. Stress is tensile force. So that's, stress is here. So that's the definition of the first one there, tensile force, and that drives the rest of the material's behaviors. So that's the great mover, stress, and depending on how much stress the material is under, the material is going to be this, that, and whatever else. Okay, so the rest of them will unfold based on the magnitude of this stress. Like I said, I'm not going to have a number for this force, for its magnitude, but the concept of magnitude of force is not going away. So its direction is important, but now its magnitude is coming in just a sec. So force drives everything, and the material's reaction as it's being under pressure is that, I'll just go to red, is that it shortens or it stretches. But instead of stretches, another Latin word is used here, elongates. So I'm going to write that one here, elongation. How about elongation? Yeah, shortening and elongation. It shortens and it elongates. You get the idea. Now, solids, liquids, gases, there, gases, liquids, solids, they can all be under pressure and they can all be in stress. Gases can be under pressure, very straightforward. First aid, oxygen in a cylinder. It's a compressed gas. in a pressure vessel for the paramedic to have the oxygen for a casualty. The same with welding gases or propane for the barbecue. It's all a pressure vessel, compressed gases. You see how these words form a sentence there, or parts of sentences. Liquids can also be pressurized. Soda pop. Alright, now in a soda can, the pressurized gases will pressurize the liquid, and the liquid has nowhere to go. Everybody stays put, but the liquid is certainly pressurized. If the liquid is free to move, then it's a splash. Say you drive through a puddle, and the liquid underneath the pressure of the vehicle, it's gonna go wherever it can. Okay, that's gonna be a splash. And solids are also under pressure. If it's not a puddle, if it's a manhole cover, when you drive over it while the wheel is on it and the tire, under the area of the tire's contact patch, the solid is under pressure. When the tire patch is not on it, then it's not under pressure anymore. And while gases, liquids and solids are under pressure, they shorten. It's measurable. It's not complicated. It's very straightforward, measurable. The same applies to stresses. Now, you don't pull on gases too much, but you can pump gases from one location to another using vacuum, and you can use stress on gases, and same for liquids. You don't usually pull on liquids, but they can be pumped from A to B. On solids is what our main consideration for stress. Solids can be stressed, very straightforward. Here is a chain I found on the road, and here the chain is at rest in my hand, so this would be at rest, and now the stretch of or length of chain between my hands is in tension, very straightforward. And as it is in tension, it elongates, not by much, you know, little force, little elongation, big force, big elongation. So forces in both of these directions, depending on their magnitude, drive all of the other definitions. And this is how the journey unfolds, because it's a journey caused by forces that ends with the material's failure. So between no load and or no force, or load is another synonym for force. Okay, I'm going to write it as well. And I don't know, green. Force is the same as load. Okay? So when there is no load on this chain, it is being described as at rest. No force is acting on it. It will stay at rest. And forces are applied on it. And when a great enough force is applied on the chain, it will fail. So it's a journey from rest to failure. So these 8 words take place in this context, along this journey from no load to failure. Okay, all of them. So the journey starts with materials that are flexible. Okay, I'll write it. Okay, flexible. Or some other materials are brittle. The difference between the materials is, and this could be, a material could be flexible in compression, it could be flexible in tension. Some materials are flexible in compression and brittle in tension, or the other way around. Same stuff. Compression and tension both apply to brittle materials. They can be broken in compression, they can be broken in tension. And flexible, the difference between flexible and brittle is that the materials under forces either shorten much or elongate much. If they have a lot of give, That's not a material science word, but that's an English everyday use. If they have a lot of give, if they elongate much, they're flexible. If they elongate just little and then bam, they fail suddenly, and then they're brittle. Okay, but they all elongate and they all behave measurably elongate or shorten. So here is a block of eraser. This can elongate in tension. This can shorten in compression. There it's kind of buckling a little bit, but you get it. The definition of flexible is a material is able to bend, stretch, or twist much. Definition for brittle, it doesn't do those. It doesn't do much of it. Here is ice cream cone. Ice cream cone is made of material. When a force is applied on it, it doesn't, I'm pulling on it, it doesn't elongate much, and then it breaks suddenly when it's done elongating. Here is a slice of bread. There, it's from the Polish deli. It's flexible, and when I pull on it, it elongates more than the ice cream cone. Eventually it does fail too. Everything fails, and most materials actually fail in tension. Whether they are brittle or flexible, most materials fail in tension. The overwhelming majority of materials, and only really a few of them fail in compression. Think about this chain. You can tear it apart by pulling with a great enough force on it in tension, but in compression, you see, you can roll it up into a ball and compress it. Eventually you can liquefy it, but you know, it's not going to fail in compression too soon. Same stuff with how about the sheet of paper? I got this sheet of paper here. Okay, you can compress it like so. It's compressed, and you can compress it even more, and you compress it into this tiny little thing. It's still compressible, and it'll still be fine, not really failing, but here, same kind of piece of paper, when you pull on it, it doesn't need a whole lot of tensile force to separate the paper components from each other. But if your compressive force is being applied, it's not going to separate and break. It's just going to be shortening and shortening and shortening. Eventually it will liquefy. So, flexible materials, definition for flexible is here. Able to twist, they're able to twist, bend, or stretch much. Maybe not without breaking, but yeah, without breaking or way before breaking. See, it's in the journey between no load and failure at the far end. So flexible materials do this a lot or much, and brittle materials do not deform much. So in this sentence, how much? We'll crunch some numbers. I'll get some. There will be numbers, but much is dependent on the amount of force, the magnitude of force that's being applied. And in the sentence deform here, the deform replaces twist, stretch, and bend. So you can also say materials don't stretch, bend, and twist much, or just shorten it. Fewer words to read and write. Materials doesn't deform much. So I could have brought in a cracker, but I want to eat a chocolate ice cream, so I had an ice cream cone. And the bread, that's just standard supply here. So that's flexible and brittle. Whether the material is flexible and brittle, the only difference again is that when force is applied, they shorten much or shorten little, or elongate much or elongate little. Either which way, the materials along this journey that ends with failure here, fail and fail, it's torn apart. This journey starts with E. Materials are being elastic first. So, way before the bread breaks, here is the other slice. isn't broken. Yeah, there's this one. Way before the bread breaks, the bread elongates. You can see that it elongates. It's also on the eraser, it elongates, and I can compress it. So first, materials are being elastic. Definition for elastic is that the material deforms temporarily. It deforms under a load, same as force, and it does return to original shape and size. See, you can stretch on this bread within reason, and it returns to original shape and size. The first stage of journey when the magnitude of force is little. Same stuff, you can stretch on it, it needs a little more force, but you can stretch on it, you can compress it, and it returns to original shape and size. If this is a 50 millimeter long block of eraser, it returns to a 50 millimeter length. This elongation and shortening will be measured, very straightforward. Super easy to measure it with a plain ruler. So that's the first stage of the journey. When the elastic limits of the materials are exceeded, materials deform plastically. Plastic deformation is permanent. Stuff is permanently ruined in plastic deformation. I can't really compress it enough to make it permanently shorter or stretch it to make it permanently longer, but I have something I can. Here is this spring here from a pen. It's a shorty one. This pen used to be in a pen, and I'm gonna destroy it now or elongate it. So in compression it will never fail, and it's gonna be elastic in compression for a good while, but in tension, when I pull on it, it returns to original shape and size if small enough force is applied on it. But after when enough force is applied on the thing, it moves to a permanent plastic deformation. So if I pull on it too much, it stays or gets longer and stays that length. It does not return to original shape and size. It didn't fail yet. It's still a wire from which this coil was made. It failed as a spring, but it didn't fail as a material. Okay, it failed as for its function inside a pen, but the material didn't break yet. It just permanently deformed. So it's in its plastic range of deformation, and here is plastic deformation. A material deforms plastic permanently when it's plastic. Deforms under load. It does not return to original shape and size. So there's that. So far we covered this much, that the stresses drive shortening or elongation, and materials can be either flexible or there's brittle, either which way, and deformation first is temporary, so that's done, and deformation after that gets permanent, and that's plastic. Okay, so far we covered these ones. Next one, malleable and ductile is the next. So from a permanent plastic deformation, whether depending on if it's compression that's being applied to the material or tension, materials permanent and plastic deformation can be described with these two words. Can be malleable or ductile. Malleable and ductile are adjectives of this thing, so it's not after this journey. So maybe I should, instead of arrows, oh, that's too bad, we'll fix it. Instead of arrows, I'm just gonna go with there, two straight lines. So those are adjectives that describe this plastic deformation. If the plastic deformation was done with a compressive force, that one, then it was a malleable plastic deformation. If the deformation was done with a tensile force, it's a ductile plastic deformation. But ductile and plastic, these words are not doubled. If somebody says, oh, it's a ductile deformation, everybody gets it, that it's already past its elastic range and it's in the permanent, and this permanency is produced by a pull. The same applies to, I'm going to do it the same way, same applies to brittle materials. They all, so I'm just going to go M and D, malleable and ductile, so that's the same idea. Brittle materials such as glass. Glass also elongates when you have a shock wave or whatever, it flexes in the frame a little bit. It has an elastic range. If the elastic range is exceeded, then the deformation will be permanent. It's plastically deforms, and the plastic deformation could be, in case of a glass, it's not the shock wave. Glass's plastic deformation is when its thickness changes, it's installed vertically and it's getting thinner up top and getting fatter down there. It's a permanent change in size. It's measurable that its original thickness is thinner up top and thicker down below. It's a brittle materials, very slow plastic deformation. Okay, so flexible materials and brittle materials can all be pulled or pushed and deform permanently. So some cases are more spectacular or happen more often than others. And last here, oops, we'll fix the typo there. Like I said, the journey ends in failure when the plasticity limit of the material is also exceeded by a tensile force or a compressive force. Then the material will fail. Flexible materials fail, brittle materials fail, everything fails. The same for these guys, they all end up in failure. So, definition for malleable, and we are doing the last two, this one here, malleable and ductile, and then we'll deal with strain. The malleable and ductile is over here. Malleable means that the let's get rid of this screen, maybe scroll up a little bit there. Malleable means that the material deforms permanently in compression, and ductile means that the material deforms permanently under tension. And eventually, when there's enough deformation is done, eventually it all goes to failure. Both of these cases can go to failure. So those are the definitions. We are doing the last definition, which is strain. So where is strain in all of this? Along the material's journey, as it shortens or elongates, that's where strain comes in. So I'm going to do another slide here. Say the material's initial length or original length, and L is just length, is and some people abbreviate it as LO, length original. I don't like LO because it looks like a zero. I like length initial. There. Say the initial length of the eraser is 50 millimeters. Everything is millimeters, okay? I'm not going to print mm everywhere. Initial length is 50. Say I stretch this thing and it elongates under some force, under some tensile force. And its final length is 55. In this case, when you do a subtraction, then the elongation that took place is 5 millimeters. Now that math is not groundbreaking, but those are the abbreviations and symbols that work with the terminology, and we're getting to strain. What we have here for elongation, for 5, it's important to notice that this is a business of subtraction here. So 5 in terms of math is difference in length. Not just change of length, because change can go any way. Change can go can be compressed or can be stretched, but this difference in length is written down as triangle L. Okay, what the hell is triangle L? We're getting to it. So this triangle L, if you read it as a triangle L, you're going to be laughed around for a couple of weeks, but this is a Greek letter. That's the Greek letter delta. Delta means difference of. Okay, I have here a Greek alphabet happening on this slide here, and let's go red, and there is the Greek capital delta. It's pronounced as delta, as in thorough, but if you don't want to pronounce it that way, you say delta as in Douglas. I don't care, right? So I'm going to use delta. So this delta L is 5. And there will be some more Greek letters coming up, so don't go nowhere. That Greek alphabet isn't going away. Why is it not D? Because D is used for diameter, diagonal, and other things such as differential. So we're not doing differential equations, and so we ran out of the uses of the letter D, and it's just this difference in length is just delta L, or in short, elongation. So you can read it as delta L is 5 or elongation is 5. Now, where is strain? Strain is marked with the letter epsilon. That's lowercase epsilon. It looks like an E, but it's kind of strange. Epsilon is right next to delta, and it's here. That's Greek lowercase epsilon, and it makes the E sounds, as in egg, okay? And this delta makes the sound, as in thorough, okay? So epsilon is strain. See, this material that's elongating is straining, but elongating and straining is different slightly. So strain is the quotient of, and there's going to be a division here, because quotient is the result of division. So the definition of strain is that strain is the quotient of delta L. Strain is the quotient of elongation and something that goes there to be the divisor in this division, because that's the dividend, the number to be divided. It needs a divisor, and that's going to be the quotient. So where is the divisor? The divisor is this number here, very straightforward, yonder, length. So you can put in length, or length initial, length original, or either which way, but strain is the quotient of difference in length, or elongation and length. Okay, strain is the quotient of elongation and length. Let's go to the definition page. Do we have strain here? Nah, no, it isn't. So that's what it is. Just write it down. Strain is the quotient of elongation and length. Which length? That one. Initial length or original length. And I know we exceeded the 30-minute limit, but we're almost done here. From this strain, we can calculate elongation. We can calculate elongation percent. Say this stuff, this eraser example, elongated, that was 5, there 5 out of 50. It elongated 5 mils out of 50, and strain, therefore, it doesn't have a unit of measure, because this is millimeters and that's millimeters, and millimeters divided by millimeters is, just leave it alone. So strain is 0.1. Yeah, because 5 out of 50, okay, let's do equivalent fractions. 5 out of 50 is the same as 10 out of 100. 10 out of 100 is 0.1. Yeah, so strain is 0.1. And elongation percent, okay, by what percent did the eraser get longer? By 10%. Or how did we get 10%? Oh, 10 or 5 over 100 is 0.1 times 100 is gonna get you 10. So there is elongation percent based on strain. Alright, very straightforward. We'll be doing percentages and everything, but this is two simple measurements: length initial, length final, do a subtraction, and then do a division. So that's what strain is, and we're basically done with all of the definitions, except one more Greek letter. What drives strain is stress. Okay, and stress also has a Greek letter. Where do I write it? I'm going to write it over here. Stress has a Greek letter, and it looks like this. It looks like an O with a little horizontal line above it. It doesn't have a baseball cap. It's just, that's how the letter looks like, and that's the Greek letter sigma, lowercase sigma, that one there. Now, why do we have two lowercase sigmas? Because that one is mid-word and that one is a sigma that's word ending. Okay, then that one is the uppercase sigma. That's used for sums, as in, you know, 2 plus 3 equals 5. 5 is the sum of 2 and 3, that kind of sum. And that sigma is not used for anything in math or physics, but that sigma is. Okay, so strain is epsilon and stress is sigma. Don't mix them up, and don't get lost with stress and strain and sigma and epsilon, because there's going to be more math with sigmas and epsilons. Okay, so that's how these letters are led: delta, epsilon, and sigma, and that's how the math is done. Fairly straightforward. The same math works for compression, but the difference in length will be then it's a +5 if it didn't elongate, it's a -5 if it didn't elongate, if it compressed. It's just initially is 50, final is 45, so then you have a difference in length of -5. Same stuff, just everything backwards or with negative numbers. So that's how these terms, let's just go back to the first slide, that one, that's how all of these, so that was strain, okay? The quotient of elongation and length, and so that's how all of them work together. Stress driving all of these other changes in material and behaviors of material until they all go to fail. The material elongates and strains and elongates more and more and more, and then it fails. So that's the journey that the material does, and along the journey it can be flexible, it can be brittle, it can be in its journey in the elastic range, it could be found in its plastic range. The plastic deformation could be brought on by ductile forces or by malleable forces, and if those forces keep increasing, material will fail. That's where its journey ends. Thank you very much for watching, everybody else in here. Let's go for a leg stretcher break, shall we?